Inferential statistics let you draw conclusions about populations by using small samples. Consequently, inferential statistics provides enormous benefits because typically you can't measure an entire population. However, to gain these benefits, you must understand the relationship between populations, subpopulations, population parameters, samples, and sample statistics. Inferential statistics takes data from a sample and makes inferences about a larger population which the sample was drawn. Let's define population and sample. We're going to start with population. Think of population as everyone. So let's say it could be everybody at your school, everybody in the United States. The greatest one on this one is the census. Okay? But unfortunately, not everybody will take the census for whatever reason. So it can be a large group of people. It could be a whole bunch of people at church. It could be a whole bunch of people at school, a whole bunch of people at the mall. It doesn't matter. But you're going to take everybody. So on that day, you take every person has to do it in the mall to do a population. Okay? Bigger than that, every person that steps inside of a mall on, let's say, October 1st is going to take this survey. It's not truly realistic. So let's talk about a sample. Okay? A sample is basically a small portion of this group. So you can say it's about this many people. Generally, the minimum size is 30. Okay, and each test has a certain number of people, a certain number of participants that you have to use. Each one of these in the sample is a participant, and you'll hear me say this a lot this semester, is a participant. Each one of these participants is important to the group of the sample. So now, once let's say we've taken this group out of this population, we've done this, now we run our test, whatever that test is. Okay, and then when we're done analyzing the data, okay, this will send us back to the population, and we will infer that the results from this actually point to what everything is happening in this group. Because the goal of inferential statistics is to draw conclusions from a sample and then generalize them to a larger population. We need to have confidence that our sample accurately reflects the population. And in the last segment, it shows exactly how you can do that. This requirement affects our process. On a broad level, we must do the following. Define the population. We have to understand everything about the population. Draw a sample. And use the perfect test. Descriptive statistics describe a sample. It's pretty straightforward. You simply take a group that you're interested in, record data about the group members, and then use summary statistics and graphs to present the group. With descriptive statistics, there is no uncertainty because you're describing only the people or items that you're actually measuring. You're not trying to find out and infer properties about a larger population. The process involves taking potentially large numbers of data, in a various sample and reducing them down to a few meaningful summary values and graphs. This procedure allows us to gain more insight and visualize the data than simply pouring through rows and rows of raw numbers. In descriptive statistics, think of it this way. If I am, let's say I go to the doctor's office and I put my name, well, I'm not going to say name because we don't use name, but age, gender. They may ask insurance company. They may ask, and you get some places you go, they get the long one where they ask you all about your health history. Okay, anything like that. These are all descriptive statistics. So this is not, when you go in there, that's not just stuff you have to write down so they know it. They can look at everything that they have. How many males and females do they have? How many people are from this insurance company? How many people are that insurance company? So if I've only got 2 people in this one insurance company, but I'm not making any money in that one, I might be able to bring in another insurance company that may give us tons and tons of clients and fill the rooms. They have the health history. They can know how many of their people have heart problems. How many people do they have that have knee problems or asthma in this? Not only does that do that, but in an individual sense, it helps them to help that patient. But on the other end, they can see how many of their patients actually have heart problems, or how many of their patients are coming in with certain types of ailments, and they all have the same thing. Then you're going to be able to infer that to the larger population and say that all these people that came out with this might have this too. Generalization is the key word. In statistics, a lot of times it's not a direct answer. It is a generalization of the data that you have right in front of you. Okay? Once you understand the data right in front of you, then you can infer to other conclusions based on the other data that you have. Hopefully that makes good sense, because if you can grasp this concept that you're not going to come up with a direct answer, but you're going to have a generalization of a sample towards a population. This, coupled with the inferential statistics, now takes you to the next level where you're able to take the participants' background and information and then grow it to where you're running a test, and you'll be able to take the information that you have on the descriptive side, run it with an inferential test, and when you put the two together, now you draw a great conclusion. Or not. Sometimes you'll have absolutely no conclusion, and that's okay too. Each way you have something to write about. And that's the key. You'll have something to write about to draw a conclusion. Either it was conclusive in terms of the generalization, or it was inconclusive, which means either there's lots of things that could be wrong. Your questions were not formatted correctly. You may not have asked enough questions. There are many ways that can happen, and we'll talk about that a little later in the semester. As we begin to look at data, there are 2 types, discrete and continuous. Okay? These are numerical data. As a general rule, discretes are counts and continuous are measures. Discrete data is a count, can't be made more precise. Typically it involves integers. For instance, the number of children or adults or pets in your family is discrete data, because you're counting whole indivisible entities. You can't have 2.5 kids and you can't have 1.3 pets. Continuous data, on the other hand, can be divided and reduced to finer and finer levels. For example, you can measure the height of your kids progressively, more precise scales, meters, centimeters, millimeters, and beyond. So height is continuous data. If I tally the number of individual jujubes in a box, that number is a discrete piece of data. If I use a scale to measure the weight of each of the jujubes, the weight of the entire box. That is continuous data. When you classify or categorize something, you create qualitative or attribute data. There are 3 types of qualitative data. The first one is binary data, where we place things in one of 2 mutual exclusive categories. We could do right, wrong, yes, no, true, false. Independent, you're either right or you're wrong, yes or no. There is no maybes, in other words. It's only 2 categories. You can only be placed in one of them, but there are 2 categories. You could also do something like accept or reject. Occasionally, in the idea of the jujubes example, I get a box that contains a couple of individual pieces which are either too hard or too dry. So we're hard or dry. Okay? And I can place those in the idea of good and bad. This would be binary data. I can use this kind of data to develop a statistical model, predict how frequently I can expect to get a bad jujube. The next qualitative flavor. When collecting unordered or nominal data, we put them into categories that do not have an implicit or natural value or rank. If I went through that same box of jujubes and recorded the color of each of them on my worksheet, this would be nominal data. This kind of data can be used in many different ways. For instance, I could use a chi-squared analysis, which you'll learn later, to see if there's a statistically significant difference between the amounts of each color in the box. So understanding that nominal is basically a category. Okay? It's unordered. So other things that are nominal data, names. So you can't have a number. In SPSS, we can take all those names and give them a number to be able to count them up, but it still comes back to the name. Different than the yes and no. Okay, those are still categories, and so are these categories, but these are direct categories that go to a certain thing. You could have 50 things and have 50 different names. You could get a couple Stevens every once in a while or a couple Johns, but you have unordered data. Think of nominal as being straight words. Okay? When you move into SPSS, this is where the problem comes in. Understanding between nominal and, let's say, ordinal or ratio. When you're talking about nominal data itself, okay, nominal data would be a name, okay? It would be a color. It would be something like that, something that actually it has, can't really be used as a number. We also have ordered or ordinal data, is items assigned to categories that do have some kind of explicit natural order, such as short, medium, or tall. Another example would be a survey question, and this would be a Likert scale. This could be 1 to 5, 1 to 10, 1 to 3. You'll see this on, let's say, professor evaluations. How do you rate your professor from 1 to 5 if he knows his material? Okay, this is ordered. It's direct order. You're going to pick a number, and that's what you're going to go with. In this section, we will examine data. In statistics, there are many ways to examine the data. We can analyze the numbers. We can examine graphs to understand the shape of the data. If you are a visual person, you will love the graphs like me. I tell a story with a picture. We're going to start talking about central tendencies. Central tendency, use of the mean or the median to locate the center of the data set. And I'm basically going to tell you where most of the values fall. The first one we're going to talk about is the mean. Probably one of the more important ones. It's also relatively easy because we've talked about the mean so many times in so many of our classes. You can see it everywhere you go. in terms of on TV, they'll say the mean average. So if we understand what the mean is, it's going to be where a lot of your analysis comes from. So understanding this point is extremely important. Okay? The mean describes an entire sample with a single number that represents the center of the data. Okay? We're also talking about the average. That is the true definition, of arithmetic average. In this case, for the mean, you calculate the mean by adding up all the observations. You calculate the mean by adding up all the observations and then dividing by the total number of observations. Okay? You add up all the observations and you divide it by the total number. So let me give you an example of this. Let's say I have 5 apples. And we're going to stay with apples for a little while. Okay? In this case, we have 5 plus 5 plus 6 plus 7 plus 8. Okay? And that would be the total of all the observations. So let's add that up. That's 10, 16, 23, and 23, and that would be 31. Okay? 31. Okay? And then we're going to take it by the 5. And that would be 6.4. This right here would be our mean. Visually, you can see that it's going to be around the number 6 because it's in the center. This is your average of all your numbers. It's also the center. Okay? So if I drew it out on a number line and I put 1 to 31, I'm going to find out the 6.4 is in the middle. The mean is sensitive to skewed data and extreme values. For data sets with these properties, the mean gets pulled away from the center of data. In these cases, the mean can be misleading because most of the common values in the distribution might not be near the mean. We're going to talk about this in a little bit, but if you remember that portion of it for when we talk about outliers, it will make a lot of sense. The median is the middle of the data. Half of the observations are less or equal to it, and half of the observations are greater than or equal to it. The median is equivalent to the second quartile or 50th percentile. It's a lot of words, okay? It's basically the middle number.